components of vectors, it becomes very useful to break vectors into components. Traditionally horizontal and vertical, it doesn't have to be that. Certainly when it comes to dealing with motion, we do that a lot. So let's define a few more things. A unit vector. So it's simply a vector that has magnitude 1. So it's whatever the unit happens to be, it's that length. Okay? So every vector, except for the zero vector, will have a corresponding unit vector. Basically it goes in the same direction, but its length is 1 unit, whatever the unit happens to be. So if we wanted to calculate that unit vector, and the symbol we use for unit vector is the caret, so we have a caret and a tilde. Whoa, very fancy. So it'll basically be the vector A divided by the magnitude of the vector. And so that will then turn the magnitude of the unit vector into 1. So I'll guarantee it's equal to 1. Now there's two very special ones that we deal with, and that's what I was just talking about before, about, well, normally we do it horizontal and vertical, but we always do it so that they're perpendicular to each other. As I say, it doesn't have to be horizontal and vertical, but conveniently we use that a lot. So we have OI, which is the horizontal unit vector, and OJ, which is the vertical unit vector. All right, so we get our position vector. I'll just conveniently draw up an axis there. So there's our position vector. It's anchored to the origin, making it a position vector rather than a displacement vector. And we say, well, we can break that up into its components. So let's say this is the vector U. So U is the vector OP, that's the position vector. I could write it as an ordered pair, which is what we used to see, coordinates. We could also write it as a column vector, so XY. Column vectors, sometimes they use square brackets rather than the parentheses. But now we can also put it in component form, where we break it up into its horizontal component and its vertical component. And so it would be whatever the coordinates are, x times the unit vector in the horizontal direction, and y times the unit vector in the vertical direction. So they're the different ways we could write our vector. So the length of our vector then, well, call it the distance formula, call it Pythagoras' theorem, call it what you like. It's the square root of x squared plus y squared. And the direction would be theta, and just like in trig and coordinate geometry, we always do it to the positive x-axis, so the angle of inclination that way. So the direction would be theta, and so the inverse tan of y over x, whatever that happens to be. Equal vectors basically are vectors that have the same magnitude and direction. So there's a particular vector, that one would be equal to it. So would that one. I could draw infinitely many vectors that are equal to it. If you ever want to work out the position vector, remember the position vector is when it's anchored to the origin. So if it's been moved somewhere and you want to work out what that position vector would have been, head minus tail. Whatever the head is minus whatever the tail is. The reason that works is because when it is in the correct position for a position vector, you'd be going head minus tail, but the tail is 0. So you're subtracting 0 and you get the answer. So let's say we know those points A and B. Then we could work it out by saying, well, that's going to be 3, 0, minus 0, negative 4. 3, 4. So in other words, the head of that position vector there, we know would be the coordinate 3, 4. CD, and it would have the same answer. We also get 3, 4, because they're equal vectors. Okay. So if I wanted to write that in component form then, that vector P I know is 3i plus 4j. The unit vector would be 1/5 of P, because the length, I conveniently picked it so it was a Pythagorean triad there to make it easy. We know the length of that vector would be 5. So it would be 1/5 of P, and in component form then would be 3/5 I plus 4/5 j. I have no idea why I put the 4/5 in parentheses, but not the 3/5 or vice versa. There's 8b.